So my name is Victoria Gammathaler, and this is CE 6370, which is Design and Analysis of Reconfigurable Systems. The project is design of combinational logic designs using schematic entry and Verilog or VHDL using Intel Quartus Prime. This software here is Quartus Prime Lite Edition, and the first design is a 1-bit full adder. Here is the source code, which is generated from the schematic, and then here is the test bench, which is here, and this is testing all input combinations. And then next is to start compilation, and this will compile, and then I will be back when it finishes compiling. Okay, it finished compiling, and I also am showing the schematic for the 1-bit adder. So here's your inputs, A, B, C, N, your outputs, and then you have 2 XOR gates, an OR gate, and 2 AND gates here. So there's the schematic, and then it finished compiling. So analysis and synthesis, and then going to resource usage summary to get number of ALMs, 1, number of ALUTs, 2, dedicated logic registers, also flip-flops, 0, input-output pins, 5, DSP block, 0. Okay, and then next you have we go to the timing analyzer under tools, and then going down to report path, which is here, and you want to run your entire report path, so the longest path, your critical path. The critical path delay is 6.64, which is from element A to S, so 6.64 nanoseconds. And then closing that, next, so this was the schematic, from the schematic to get this source code. Next we are going to look at the generating from RTL, so open project, RTL, and then waiting for Quartus to load the RTL, and I'm also realizing I didn't show the waveform, so give me 1 second to get the waveform up. Okay, we're getting our waveform from Questa, and I can show you which buttons to press to get that. But within Questa, you press compile. Once Questa finishes loading, compile. Then you press your you select your test bench, press compile, done. Under work, you have your file. Then waiting for Questa, and then dragging these over. Okay. Then go down to 1 nanosecond, because that is what we used in our test bench. Run all, zooming in, and this is a schematic, by the way, or from schematic, and then this is correct because CN, if that is the only bit that is on or 1, then your Cout, or sorry, your sum is 1, your Cout is 0, and then if you have 2 that are on, which is this is B and CN, then Cout is 1. So this waveform is correct, so the logic is correct. Yes, I want to quit. And how to bring up the waveform, so run simulation tool, and then RTL simulation, and that is what I had pressed. Now going back to open project, getting the RTL file, and it is opening. And next we will compile our design once it opens, which it has. Okay, processing, start compilation, and once this finishes, then I will show you the results there. Okay, compilation has finished. Just something to take of note, the family is Cyclone V, and this is the device name. But looking back at the results. So resource usage summary. So 1 ALM and 2 ALUTs, 0 logic registers, 5 IO pins, 0 DSP blocks, which seems correct. And then going to the timing analyzer, it seems also the same as the schematic design. Port path, which should also be the same, 6.64 nanoseconds, which is the same A to some. So it's the longest path, it's the critical path. Just also look at the code. So here's the test bench, which was the same as the schematic test bench, testing all combination inputs. And then next, the full adder. So this is the architecture here. This is much faster to type rather than placing all of the AND and OR and XOR gates. This is much faster to type using the RTL design rather than the schematic design. So it's much faster. And then next step is to go to the waveform. So tools, RTL simulation. Sorry about that. Okay, so waiting for it to load. Waiting more. Okay, compile. Alright, compile and done. And in this, dragging the inputs and outputs over to the wave. 1 nanosecond. Run all. Zooming in. And yes, the correct inputs and outputs are being generated. So correct inputs, all possible inputs, and then correct outputs. So logic is correct based on the truth table. And next up, we will open project is the 4-bit adder. And first we will look at the behavioral 4-bit adder. Ignore the file names, it's the behavioral 4-bit adder. So, adder, okay. So you have there's the test bench, and for this we are I am testing the edge cases. Because if I were to test all of the input combinations, that would be 512 combinations, because you have 4 bits for A, 4 bits for B, and then 1 bit for C, so 2 to the power of 9 is 512 combinations. It's possible to test all of those combinations, but when you want to test many designs, you want to test the edge cases first, and then when you have your final design, test all cases when it's practical too. And then so 1 nanosecond here, so that's why we've been with the waveform selecting 1 nanosecond. So we're going to start the compilation process, and once that finishes, then I will be back. So alright, and the compilation was successful, 0 errors. And so going to analysis and synthesis, resource usage summary, 3 ALMs, 6 LUTs, 0 flip-flops, 14 IO pins, 0 DSP blocks. So that looks correct. And then next, tools, timing analyzer, and scrolling down to report path. And not specifying, so you get the longest path, so 7.985 nanoseconds, so that is a higher critical path than the 1-bit adder, which should be as expected because you now have 4 bits. You have to have more logic gates. So for the 4-bit adder, it's from CN to COut was the longest data path, so it's the critical path. And here's the test bench. So as said before, it was the edge cases for the full adder. This is behavioral for the full adder. And then inputs, A, B, and Cn, and sum and Cout are outputs. And then you have your calculations here, so that your sum and carry, and then these are variables because you need to use these variable steps, and then you have the Cout and sum are the actual output signals. And next, looking at the waveform to make sure that the waveform did generate correctly. When it loads. Oh, the name for this I had forgotten. These are blocking. This is non-blocking. So non-blocking just means it will execute without waiting. Basically, is what it means. So compile. Okay. Compiling the test bench. Done. Work. Open. Here. And then A to S. Okay, and then run all. Zooming in to make sure the logic is correct. Okay, so 0 plus 0 is 0, so that is correct. 1 plus 1 is 2, correct. 2 plus 2 plus carry in is 5, correct. And then another edge case, so F plus F plus 1 is F, and then 1, which is the carry over, just like 0 plus F plus 1 carry in is 0, which 0 is here, and the carry out. So carry out is because it rolled over to carry out, the sum output did. And so that is correct logic. Yes, quitting that, and then so we have verified that the design works correctly for the behavioral. Now let us look at structural. So structural. And structural just means you're using components. Just like we had designed the 1-bit adder, here's the logic of the 1-bit adder. The architecture is now structural, so you're actually using the 1-bit to make the 3-bit adder. So now we are using 1-bit adders for the 4-bit adder. So we're using 4 of those. And it is a component. So these are like the bit components, A, B, C, N, to get sum and Cout. And then you have A, B, C, N for the full adder inputs, and then sum and Cout as outputs. And then here's the test bench. Test bench is the same as in the behavioral, just testing the edge cases. So first, starting the compilation, and we will be, I will be back when the compilation finishes. Alright, compilation has finished. Going to analysis and synthesis, research user summary, 3 ALMs, 6 ALUTs, 0 flip-flops, dedicated logic registers, 14 input-output pins, 0 DSP blocks. So that all looks the same as when we had the behavioral outputs, or well, design unit, report path, critical path delay, longest path, which is 7.985, which is the same as behavioral. So the structural and behavioral designs seem to be the same from CN to Cout. And then let's look at the waveform. Run simulation tool, RTL simulation, and then waiting for Quest to open, like here. Compile. Your test bench compile done, and then under work, you now see the full adder 1-bit and the full adder, which is the 4-bit. So that is just something that you'll see with structural, that you should see with structural. And then once it loads, please load, please. Okay. It's being optimized, so I have to wait for it to finish. Once this finishes, which I'm hoping is soon. Okay, usually doesn't take this long, so I'm a little bit confused. Alright, I'm gonna wait for it to finish. Okay, now it's back to working properly. Sorry about that. I had to close and reopen it. So, 1 nanosecond run all. Zooming in. Okay, so logic is correct. 0 plus 0 equals 0. 1 plus 1 equals 2. 4 plus 4 plus carry in is 9. And then f plus 1 is f and a carry out. And then a plus 5 is the carry out rollover, so to 0. So logic is correct, which is good. Yes, quitting this. So logic is correct. Okay, so therefore we have proven for the 1-bit that resource utilization is the same in number of ALMs and ALUTs, flip-flops, etc. And for the critical path delay, the 1-bit is the same for the schematic versus the RTL code, or VHDL code used in this case. And then for the 4-bit adder, we tried a behavioral design and a structural design, and we got the same design resource utilization and critical path delay. Another thing to take of note is for a schematic design, that was only a design of a 1-bit adder. However, with more complex designs, a schematic becomes very massive and time-consuming to design. So therefore, RTL code design, like the VHDL, is much less time-consuming to get, in this case, the same design outputs. So that is just something to take of note. And that is it. So the other thing to take of note is between the 1-bit adder to the 4-bit adder, more resources used, and then more critical path delay, so more delay time of the unit, which makes sense because there is more logic gate and resources used. But that is all for this project, and I hope you have a good day. Thank you for watching.